Krishna to do the intro.
Okay.
Awesome.
Do you want to maybe share screen and test it out?
Yeah. Okay, so I think I shared on screen. So I have too many PowerPoints open, I cannot identify which one is the correct one. So maybe let me share the whole screen. Okay, you see the slides?
Yeah.
Okay.
Perfect.
Should I start or are you waiting for some?
Go for it, Krishna.
Cool. So we're at our midway point for this semester's seminar series. And today we have Deepak Pathak. He's an assistant prof at CMU, but before that, he was a PhD student at Berkeley and also spent some time at Berkeley and at FAIR. And all of us probably know him for his work on curiosity-driven exploration and a lot of other similar themes. He's won a number of awards, both as a PhD student and as faculty now, and really looking forward to hearing all about his newest work. His talk's titled Robots That Learn to Generalize Beyond the Training Distribution. Over to you, Deepak.
Okay, thank you, Krishna, for the invitation. And okay, let me start. So the main theme that drives the work in our group and has been driving my own research for several years is this belief that that generalization is what makes humans or any biological animals intelligent, and the ability to adapt to new and unseen scenarios. So in deep learning and in machine learning in general, we have seen a lot of progress in the last several years, from playing complex games to speech to language from images and cars that can drive themselves. But all this progress is nowhere close to or even like humans or other biological agents. And the key difference is that these systems are special purposely designed for the application that they're intended to be applied to. So for instance, a system that can play a complex game of Go is completely different than a system that drives a car. And perhaps it's not quite reasonable for me to ask for an algorithm to generalize from playing Go to driving a car. So let me give an example which is closer to home. Even like the most simple example of supervised learning. So for instance, let's take example of image classification, which is the crown jewel in the success of machine learning, where given the input image, we learn a model to output certain classes, like in this case, Labrador. The way we train these models is by showing a lot of images of dogs, like one more image, more images, and lots of images, which come from a giant data set, which has randomly split into training and test. Now we all know that the accuracy on these tasks is superhuman and like just unimaginable like 10 to 15 years ago. But the question is how well even the best of the models in machine learning generalize beyond what they're trained for. So I take this model and then I test it on a video from YouTube, like this here. Now this is a ResNet model and it finds things like cobra snake, ray fish, flatworm on different frames of the video, right? And this is not even a joke result. It's a real result from a real model. Now what is going on? Well, if you ask a computer vision person, then the answer will be very, very trivial. The answer is, well, the model did not see such variations of objects in the training time. And the distribution of videos and images is very different. Like images have bias of the photographer and lighting conditions and all that, which are not in the video case. In fact, that is very true. But this is the main point of my talk today. Like, no matter what we do, we'll never be able to capture all the variations at training time. So in fact, every machine learning system starts with this assumption that over here I forgot to say, like, imagine that test accuracy is still 80%, but the result on these videos is way less than the test accuracy. So this is so because we start with the assumption in machine learning that our training distribution and test distribution basically belongs to the same family. And in real world, this assumption gets falsified all the time. So even the best of the systems that work very well in the training time completely fail to generalize to new scenarios at test time. And this failure is even more expensive in case of robots, where we have hardware and all those issues may come up. So in this talk, I'll focus on the main theme being generalization, but generalization to unseen situations or scenarios which a robot is never trained for. And there are many axes to this question of generalization. So for instance, you could think of generalization across goals. If you're thinking of an embodied agent, like, oh, I was trained for something, can I generalize to a new task? And this kind of generalization is more of a cognitive generalization, I would say. It could be more of an abstract level thing that you are thinking of new goals and new scenarios, etc. But there could be other forms of generalization. For instance, transfer of skills or policies across hardware or across robots. And this is something which probably we don't have to worry about as much as humans. But if we think of not at the lifetime of the agent, but lifetime of different animals over the course of evolution, things do transfer from one setting to other setting. Like, there are animals out there which can just walk as soon as they are born. And I'll show some examples in the talk later today. So we do want generalization across different kind of robots. In fact, this is very critical from a practical point of view, because every lab has a different robot, and everyone has their own robot stack, and they know everything. And it's very hard to transfer things across scenarios. Third, I will talk about generalization for dynamic tasks. So for instance, motor synergies, etc. So for instance, you might, like, the whole skill of performing some dynamic tasks like catching a ball or throwing a ball. And we can really figure out how do all these motors interact with each other in coordination to perform the same dynamic task for new situations, like new scenarios of catching a ball, which were never, which we may never have seen before in a very high frequency manner. Then finally, I talk about generalization from sim to real, where the key difference happens in case of changes in dynamics. And currently, sim to real is more like an engineering setup where we try to tune our simulators as much as possible so as to generalize to real world. But can we do it in an online fashion and in an active fashion? Okay. So this is the high-level overview of the talk today. So let me start and talk about the first part, generalization across goals. And before I go there, let's take an example here as to how do we even train a robot in general to perform one task or one goal before we talk about generalization to new goals. So let's say I have a robot here, and the robot sees this image, and it trains a policy to go to this goal image. So the idea is to train this policy to output actions such that this goal is achieved. So what are the most common ways of doing this? Well, the most common, and I would say the most successful way in robot hardware is this imitation learning, where the expert gives the data. But one catch with this is that the expert has to control the robot manually, either kinesthetically or via teleoperation, to collect all this data, which is very tedious and expensive and slow. But it has to be repeated for every new goal that the robot will have to do in the future. And this makes this impractical approach to go about this. So there has been this lot of interest in applying reinforcement learning algorithms for robotics. And the way they work is that you have this current image, and you train a policy that can output a sequence of actions to go to goal image. Now, when you reach the goal image, you get a reward function. Now, this approach is much less much less expensive from the human perspective, as in you don't require as strong of a supervision. but it has some catch. And the catch is this policy in the beginning starts being random because you start with random weights of the policy. Now, if you think about this, so when you reach some reward or the end state, you get +1. Like you reach some goal state, you get +1. Okay. Now, if the policy is random in the beginning, how likely is it the case that the robot will ever tie the knot even once in this scenario? Right? Because it's initially random. So you are relying on learning everything in an end-to-end manner. And in fact, with my estimate in this setup, because this is from one of our papers, my estimate is that it will require these many interactions to just tie the knot once. So if, and then we know about RL, it doesn't learn in one interaction. It has to learn, do same thing at least thousands of times. So this is not very feasible. And so hence the story in practice, I would say, is much less glorious. So for instance, look at these results from RL and all these games in these scenarios. They work really well. They train from pixels and output actions. But the catch is that they only look at the score of they look at the score of the game as supervision, which provides a dense reward at almost every time step. Even in tasks like navigation, where the goal is to reach some target location, most approaches today shape the reward function by providing incentives like apples in between to guide the agent. Okay, so this is what happens in practice. But in real world, there are no apples. Uh, you like the reward could be delayed by days, months, or year, such that it's hard to propagate back to where you are. So, like, how does this girl here know how to act in her childhood, so to become pilot 20 years later? Like, does she backprop gradients from the reward and then does this over hundreds of thousands of lives? Probably not. And this is what is argued by psychologists, especially developmental psychologists like Alison Gopnik, Laura Schultz, that these babies in their developmental stage, they are not driven by any sort of extrinsic goal to do something. They are rather driven by their own notion of intrinsic motivation or curiosity, where they just go out and explore and learn skills, which can then be used to solve future tasks. And in fact, this behavior of learning without goals is not only for human babies. This is actually in many intelligent species. There is one contrast between a chicken and a crow. So chickens are considered one of the dumbest animal on the planet. Like all they do their life is peck for grains, and they peck from the day they are born. The length of their childhood is like 1 day. They are born and they peck for grain, and that's what they do their whole life. On the right, you have New Caledonian crows. They have similar cortical structure and similar brain size as chickens, but they are much smarter. Like they are almost as smart as chimpanzees. And the key difference is in the length of childhood. These crows have 1.5 years of childhood, and they can do amazing things. Like they can make tools out of leaves or stems to pick up food from crevices and all that. And this correlation between the length of childhood and the intelligence of our species has been studied across a lot of primate species, and there is a stark correlation between these two factors. So this leads to our first conjecture about learn. Like maybe it is the case. Maybe it is not how you are learning. Maybe it is the fact that the lack of having any goal during learning forces you to learn something which is very generic, because you are not optimizing it for any task. You're just learning useful skills, which can later be combined together to do interesting things. But then the practical question comes up, like, oh, if there is no goal, what do you even do? Like, what do you optimize for? So can we somehow build this notion of goal-free exploration, as in the case of biological things? And this is where this is the question which got me interested in thinking about this direction several years ago. So I'll give you a very, very high-level idea. I'll not go into details because this work is still 2-3 years old. So I'll quickly move to results. But let me first describe the high-level idea as to what can you do in the absence of any such goals. So let's say you have some agent here, and you have some input that the agent sees. Let's say this image. So the example is in simulation here. And then you have some actions. So let's say 4 actions this agent can take. So there is no goal, no objective, and you just go around. Okay. So in the beginning, what happens? The agent just presses buttons like left, right, top, bottom, and it just sees what is happening in the world. And the key idea is that the agent tries to build a model of how the world works. Basically, a forward model, you would say in this case. And it is learning this model from its own observations from the raw data. And it tries to predict it tries to make predictions in the world before it takes the action. So for instance, in this case, like suppose the action to be taken is going up. It would imagine, okay, what would happen if I press up? Now it has a model, so it can predict something, or it will go up and come down. And when the same thing happens, it becomes maybe happy and it gets its belief gets reinforced. But it won't be correct all the time. Like in this scenario, if it presses up, it expects to go up and come down. But because of pillar now, it will go up but does not come down. So it incurs a prediction error using its own model. And what we can do is we can use this idea of prediction error to kind of simulate this notion of curiosity, where the agent tries to curious about things which are difficult to predict. Okay, so the high level summary is build a model, use the model to make predictions. Wherever the prediction is bad, you lead to high curiosity. And then the main part comes up. When the agent is more curious, it goes back. It goes back and explores everything that makes it curious. And as it does so, it collects more data. And when it collects more data, the model will improve. When the model improves, the error goes down, curiosity goes down, but the agent is trying to be curious. So now it will find something else where which makes it curious. So basically, in a way, this chain reaction kind of goes on forever, and it forces the agent to always discover something new, which it cannot do, or what makes it curious. And as soon as it can do it, it has to find something else. Okay. There are various formulations of exploration that have been proposed in the past before this work, but most of them were in the context of some external goal, like trying to achieve some sparse goal or something. But the difference here is we do not have any goal, and we remove the complete notion of goal altogether at this time. And by goal here, I meant external goal. There is still some intrinsic goal of exploration. So let's say this is the same example over here of this game. In the beginning of the training, you have no reward, nothing, no goal. So the agent just jumps around and basically is not doing much. But after this training for a day or so, this agent starts to discover interesting behaviors in the game. So it starts to go down, and it just starts to play the game as a side effect. In fact, it crosses 11 levels of the game without having any knowledge of what the game is about, or what the goal is, what the task is, what the reward is. Okay. So why is this happening? Like, why is it learning these behaviors like jumping enemies, killing enemies, jumping over pipes? If you think about this, in the beginning of this scenario, dying is fun for the agent, so it dies a lot in the beginning. But then when it keeps on dying, it starts at similar location again, and it starts to predict the consequence of, oh, if it dies, you can restart or something will happen, and it can predict that stationary position. So then it tries to stay alive to be curious, and then it starts to kill enemies, because otherwise enemies kill the agent. So this is all causal, like butterfly kind of effect, which makes the agent do interesting things throughout the scenarios. So we began this idea with the game settings, and we tried on almost all the environments that people had tried RL settings on in simulation. Like Atari games, Robo School, Navigation, Wisdom, Mario. And it turned out that surprisingly across most of these scenarios, without having any reward, any supervision, this completely unsupervised agent can discover very interesting behaviors. We tried this across a bunch of environments in both continuous control to navigation to games and all that. And it turned out that it can actually do good behaviors. But now there is one catch, and the catch is that simulation and games are not real world. Like, how do you scale these methods to real world? And I'm going a bit fast over here because this work is probably you guys are more familiar with. So now the question is how, yeah.
There was just a question from the chat from Akram. Do you want to take over, Akram?
Yeah, thanks. I don't want to interrupt. Sorry. So I just had a question about the Mario setting you gave. You said it stops dying after some point, but if it reaches a new space where it could die, does it necessarily experience dying there before starting to avoid it next time, or can it generalize from the previous similar areas that since they have the same dynamics, I guess prediction would be the same maybe. Anyway, I think maybe you can elaborate on that.
No, yeah, I think you are right. So probably when it reaches the second level, so if you have played this Mario game, it has some weird thing. It has day and night thing. So day is blue, night is black. So when it goes from day to night, things fail maybe in the beginning, but then there is no notion of testing versus training. Like it can always learn with this self-supervised loss function. So it just adapts faster. So we had very thorough experiment then that if you train on level 1 and go to level 2, some skills generalize. You still need some samples to fine tune and adapt, but it adapts much faster if it had experience of level 1.
Yes.
If you so
the prediction model is kind of already pre-trained quite well on the first level, right?
So we did not make any distinction of the level. We just played it the whole game.
Yeah, sure. Yeah. Okay.
Yeah. So the result I showed, that was just run for a long time, and then maybe if you take the result slightly before that, maybe it is reaching level 5 and not level 10. But there is generalization slowly. So like if you play first level, you can do second level faster, and third level even faster, fourth level even faster. I think then 10th or 11th level will become very easy because you're just applying the skills to do those. So we do see some improvement.
There was one other question from a while back during the motivation about the knot tying about sub goals and like the role of sub goals in maybe making RL more efficient. So
I would say sub goals is not too different from like providing apples in a navigation scenario. So yeah, I think even though the question is how do you learn to go to sub goals? Because in a real world setting with these, like I can maybe give you sub goals of different stages of tying the knot, right? Then the question is still is how do I go between those sub stages? And it is super expensive to train RL in those scenarios. And I see another question. Actually,
another question, Abhishek.
Hi, my question was that take a problem of navigation where our goal is to reach our goal in a minimum possible time, like taking the shortest possible route. By intuition, like if agent is driven to explore more or generalize more due to curiosity, so it will tend to maximize its path to explore more, to keep its curiosity intact. So how would we like tackle this kind of problem?
So currently, I have not come to the part as to how do you go from goal-free exploration to achieving goals. Right. Think of it as a progression right now is we are at the baby stage. If you ask me to go and pick up food for you, it will just get lost and probably not even come back, right? So it's like that kind of stage. So I'll come to part where how do you go from this goal-free stage, which is for learning skills, to actually performing tasks that the end user want.
Okay. Thank you.
Great. I'll come to this. So first, before I go to that question, let me cover one work, like how do we scale these things beyond robots and beyond simulation to real world. And I'm not going to cover this in more detail, but here, what we did in a follow-up work to handle some of the limitations of the prior method. So there are many things I have skipped right now. Like for instance, is curiosity greedy or long-term? Because greedy will not work. You can always get stuck in a local minimum. So it's long-term. And I did not present how do we do that. But the other problem is it was relying on this reinforcement learning optimization that you have to compute prediction error. Now to compute prediction error, the robot has to act in the world and then collect next state, because the prediction error usually is the difference between the output and the actual ground truth, like xt plus 1 minus xt plus 1 hat. Now, the real world is black box. So you cannot backprop through this objective, like this prediction error objective. And which is the same case as in RL as well. You cannot backprop through rewards. So we use this reinforcement learning approximation of which is true in expectation, but not true in general empirical online case. What we did in a follow-up work is to modify the reward slightly. Now, instead of building one model of the world, the agent is building a lot of models, like let's say an ensemble of models. Each of these models are trained to output the effect of the action. So they take the current state action out to the next state, and they are trained in the same manner. But we redefine the notion of curiosity to not be the prediction error, but be the disagreement of the models. Now the disagreement function is basically the variance of all the output. Now to compute the variance of the model's output, you don't have to actually act in the world. You can directly compute it by just imagining what the next state is. And that function, this disagreement function, is completely differentiable because it does not rely, like at this stage, you don't even need this xt plus 1, which means you don't have to act in the world. So it's not black box. And this you can optimize very directly and in a very efficient manner. And by this notion, we were able to scale these approaches from simulation to real robotic scenarios. But before I go there, let me show you an example of random exploration, which is still the most common way to collect data in self-supervised robot learning setups. So if I run a robot randomly with all the right priors, that it has this predefined action space and everything, it does not even touch the object even once for a long time. So how is it the case that everyone can still publish 1,000 papers with random exploration if the robot does not even touch the object to collect any data? Well, there are two tricks that people use. One is you put lots of objects at one location so that if the robot goes and randomly acts in there, it can collect some object and collect a positive example. Second thing you do is you have lots of robots. But so to make the problem harder, we put only few objects to make it sparse so that you cannot just go randomly and interact with the data. And secondly, since it's academic problem, you cannot have more than a couple of robots. Let it be like 100 of those. But we can make the algorithm more smarter. So here we use the sample efficient or disagreement-based exploration on the robot. And then after a few hours of training, it starts to do interesting things and collect interesting data. Like it starts to pick up objects, it starts to put them together. Now note that this is all happening by looking at the image. So it's the same idea as this Mario game. You are looking at the image on the table and you are acting and applying joint angle control or applying the end effector control to the robot. So it's the same setup from images to actions, no hard coding of objects, no segmentation, nothing. And it starts to do interesting things purely by exploration. And now the question that came up earlier, how do you go from this exploration to achieving goals? And the idea is very simple. We just follow what control people have been saying for ages, is build models and do planning. So basically we explore the environment, collect data, use the data to build models, like forward model or inverse model, could be anything. And then at test time, use the model to do planning for the goal. This could be MPC or anything. Okay, but so let me show you an example over here of the same not thing before. So here the robot goes and explores the environment first. So it moves this rope and collects some data and builds model. Then at test time, I ask the robot, can you generalize and solve any of these tasks? So you show these shapes to the robot and ask it to achieve it. Now the robot is never trained for this because it is just exploring. So let's say this not time thing here. So at test time, a human comes and maybe shows an example. So we don't use all the images, we just use few images in between. And we also use just the last image as well. And the accuracy just varies depending on how many images you used. But just using the last goal image, the robot can solve this task, which I proposed in the beginning. And this is happening without ever being training for this task. This is pure generalization. The same thing you could do again for navigation as well. This robot goes and explores the environment, collect data, and via curiosity and build models. Then at test time, you give this robot some goal image to reach, and it can use its model to plan for this goal image and go there. Now note that you can obtain this result of the navigation via visual SLAM. This is a very popular area and a lot of work via using SLAM or feature matching. But the cool part here is that we never trained the robot to do this. The robot was just exploring on its own, and this behavior is completely emergent. Okay, so this is a good point to take any questions if there are. I think there was one question.
Yeah.
I have a question about predictions.
Okay.
What are we trying to predict? What kind of representation is being used for making predictions? Is it the actual pixels, the high dimensional representation, or is it some lower dimensional representation derived from it, like an embedding, perhaps?
Correct. So the main point of this past work, which I did not present because of the lack of time, is that your input should always be high dimension, like image or raw data, basically raw signal. But your predictions should not be in the raw space. You should learn an embedding and make prediction in the embedding space. So in all these works, right, so far, the predictions are happening in an embedding space where the embedding is learned in a self-supervised manner. And we tried many variants and in the papers, across the papers. So it could be you can learn the embedding by action prediction. You can learn the embedding by VAEs. You can learn the embedding by some sort of self-supervised loss or something. But usually there is not much difference between different kinds of embedding methods as long as you learn them in a right way. So it is happening in the embedding space. Okay.
Nishant?
Thanks a lot.
Yeah, hi. So my question is, I was wondering, like, what impact does the modeling errors have on exploration? Because like models can never be made to have like zero errors, and then like this could impact exploration, right?
Correct, correct. And we actually showed this as a failure point of several curiosity methods in one of the papers where the robot gets stuck changing channels of a television. Like if there's a television which shows random channels, if you press the remote and it has to navigate, the robot gets stuck doing that. And that is the flaw of a prediction error method. But the method I described later, which is disagreement, over there you are not asking the model to predict perfectly. All you are asking is for the variance to drop. So if there is something which the model can never predict, and there could be two reasons, whether it's too hard or the environment is very stochastic. In either scenarios, all the ensembles that you have, all the models you have, they will all go to mean prediction. Now that mean prediction error may not be zero, but the variance will drop. Does that make sense? Because if there is something truly random, you all predict the mean value. And when that happens, the variance drops and the agent is no longer curious. So it moves on.
Also, a follow-up question is, how do you think the capacity of the models affect the prediction error of the model?
Well, I think that question is kind of orthogonal. So it's like whatever we do for any deep learning method, like probably a deeper network is better and things like that. So we never really tune that much so if you use bigger models and you have more complex environment, it's better. So I do not have any comment which is specifically relevant to this thing. So it's a general deep learning comment there.
Got it. Thanks, Deepak.
So let's move from across goal to across robot generalization. Now, this is also very crucial, and it is kind of truly out of distribution question because every robot that we have today is different. And in my 5 minutes of Google search, I found these many robot types. And every lab has a different variant of their own robot, and they do their own thing. Right? And if we try these learning-based approaches for robot control, they are extremely finicky and sensitive to the robot's own shape or any changes in its own dynamics. Like I can train an RL agent for one environment. It already requires a lot of work, a lot of tuning, but it completely fails to generalize beyond if I change even one limb on the agent. Like I remove 1 feet and it completely failed. And there are prior works that have tried to attempt to generalize across robotic shapes, like these one here. But usually the assumption is that topology of the robot is same. So like in the left, it's hard to see the difference, but they are trying to generalize across different number of degrees of freedom on the arm. And here, this is NerveNet paper where they then generalize across number of legs. So, but it's a linear topology. But can we go beyond this and then train single policies for very different robots, like same policy for walker or humanoid, and which can control them? And the goal is to generalize to new scenarios. So now what we'll talk about is how do we generalize to new and unseen robot shapes. But instead of training on one robot or two robots, we'll train on a variety of different kinds of robot. And the goal here will be to generalize to unseen ones at test time. Okay, so what I'm arguing for here, I would say, is in some ways that the analogy to like ImageNet based training, like in computer vision. So I'm a computer vision person, or I was mostly computer vision person in the beginning. And in computer vision right now, if you have to do some new task, there is a very standard way for a new startup with new tasks. If your task is, let's say, finding boundaries and images or some classification, you go to Google, you download ResNet trained on ImageNet, you remove the last layer, you take the backbone, you go to your new domain, add the last layer, collect few examples, fine tune, and it works. And you can make millions of dollars in your startup. This is the current paradigm, right? And it works very well in practice. It's really good, and it's not. And every company is capitalizing on this, but this is nowhere the case in robotics. Like every robot or every new thing has a new policy. So what we really want is that if I have a new robot here, can I somehow already have a pre-designed controller which can work to some extent in your new robot? And the performance should improve after fine-tuning. So this is very challenging because unlike vision or language, there are different components to it. Like every robot can have different number of inputs and outputs, like limbs can be different. But the bigger problem is not this, it's this, that every robot has a different behavior. So the space of output actions you are modeling is very different. Okay, so and why should this even be possible? So we take up this problem in the domain of locomotion for now, but our goal is to extend it to manipulation as of now. So at least in locomotion, there is already evidence in biology that there are shared patterns across different species of animals. And in fact, there are animals which can just walk after birth, like in 1 or 2 hours, and they're not learning to walk. They can walk. So learning to walk versus walk is a different thing. So, and this behavior the only explanation here is that they have learned it over evolutionary process. And so this is a generalization across evolutionary scales, across hardware. So the question, first of all, before we show generalization, is how do we even train a single policy for multiple robots so as to generalize beyond training? And this line of work we began several years back, kind of in parallel to the curiosity direction. And the idea here is that instead of learning these controllers at the level of the robot, let me try to learn these controllers at the level of the motors. Okay. So, and then, so in this work was Nurip's work, which we had published a couple of years back. And the idea here was that instead of learning policies for the full robot, we evolve the hardware of the robot over time and allow these limbs to combine together. So we train a policy. So I'll just go very fast and see if it is. So I train a policy for every limb of the robot. And then these limbs can combine with each other and then do interesting things and then solve some task. The task here was standing up. And then we found that they can generalize to unseen scenarios at test time without any further fine tuning, which I'll not show here. But we apply the same idea to this problem as well of learning controller across multiple robots. So instead of learning a controller at the level of hardware, I will learn at the level of motors. Okay, so the same controller is shared across the motors of not one agent, but motors of all the agent. So any agent out of these ones, let's say this worker here, every motor will have a controller here, and this policy will be shared. This will be shared not across the motors of this agent, but motors of all the agents on the right. Something happened in the PowerPoint. Okay. And now the question is, will it just work like that? Like if I just share the policies everywhere in the motor, one thing I have handled is I have handled the fact that any agent can have arbitrary number of policies or arbitrary number of motors and it will work because I can just copy the policy multiple times to how many motors you have. But will this work? No, because I have not handled the second problem. Like there is no coordination here. So how does the robot know? Like how does the motor at the hand versus leg know how should they act and how what should they do? So to allow for this coordination, we allow these nodes to communicate with each other. But before I explain that, let's see what are we looking for here. So what are we looking for here is that we want the same policy to act at different places in the body of the robot. So we want the same policy to be at the abdomen, at head, as well as at the hands. So same policy is applied on top of on top of itself, as well as at the bottom of itself. So what I'm kind of looking for is Lego block kind of framework. Like when you have Lego blocks, let's say of same color, you can put Lego blocks on top, at bottom, and in different shapes. You can make arbitrary shapes out of Lego blocks. But our networks are not Lego block. Their input and output are not the same dimension. I cannot pass the output as input and be done with it. So what we do is we add an extra vector in these robots, and we call it message here, and we make sure that they are in the same dimension. So just an extra variable for input and output. Then I can have any robot shape, and then I'll copy this policy same number of times for each limb, and then the message of the children goes to the parent, and then parent to its own parent. And then when my policy shape changes at test time or even at training time, I can just cut the policy from here, and then I pass it to the pass this message from the bottom policy to the parent policy. So just cut it from here and paste it here. Okay. And now the question is, how does this passing of messages work? What we do in this case is we pass the messages from bottom up and then top down. So in two ways. So it collects all the information from the body in going up, goes to the root node, and then comes down from the root node. So I'll just skip this part and go to the results. Now, let me first show you how does this policy capture the behaviors across different robot types. So as you see here, I think this is quite interesting. Same policy is functioning across all of these robots and across all of their joints. And even though it's the same policy, it behaves very differently depending on if the robot has one leg or two leg, etc. Same policy everywhere, and it shows very different behaviors across the shape of the robot. Again, same policy, and you can see the drastic difference in the gaits, even though the policy is shared. So it has short leg, so it's using the front leg to move. It has no front leg, so it's dragging itself. And yeah.
With this message passing scheme, is there a requirement that there's no cycles in the graph?
Currently, in the thing, we did not assume any cycles, and the argument we gave is like there are very few biological animals which have cycles. The only example I know is of slime mold. Slime molds have cycles, but if you have cycles, you can do like belief propagation style. You can do multiple levels of passing, and then that should fix it. Yeah.
There's also a question from Puya.
Yeah, let me just two more slides and then the question. This will finish. This part will finish.
Okay, yeah, just a quick question. I think I missed it. So when you were training these blocks, what kind of shape did they have? Did you just like randomly connect them into like weird different types of connection graphs and then train on all of them?
Yeah, correct. Kind of like that. So they have these shapes. You can see in the background here, a lot of these shapes.
I see. So would you say that did you make sure that the actual test shape was never seen during training?
I haven't come to the testing yet. So they were all training.
Oh, okay.
So here is the training. Here is the testing.
Thanks.
We made sure that these shapes are not there, like these exact shapes are not there in the training, and this works. But I would say this is very boring. Because even though I can say they were not in the training, but they look almost the same. Like, why is it surprising? So what we did is we went out of our way to create something which actually looked very, very different. And so something very, very out of distribution. And here is something which you can see were not there in those examples. So we made this monstrous looking, weird shaped things and tried the policy zero shot at test time. And I mean, nothing close to this was there in the training set. So they don't excel, like they are not running forward crazily, but they are still able to do decent things. And like this robot here discovered a new thing at test time. It has very heavy hands, so it is running on its knees almost. This has 4 legs, so I don't know what it is doing. It's not even moving forward really. And then we also had objects at test time. Nothing was at training time. And again, they don't move forward particularly well, but they also don't just fall. But sometimes they fall as well. Like here, this first robot is just too heavy to walk, so it just falls on itself. Second one also has very heavy body parts, so it cannot balance. Third one does not have legs, so it tries to use its hands, but fails to move forward.
Can I ask another follow-up question?
Yeah.
Did you try to somehow quantify how different those graphs are between like test and train, and like whether like the success is kind of like what kind of function of that difference between the train and test graphs? Like I'm thinking of like what is the maximum difference between points in the training set versus the maximum that you have between test and train, something like this.
So we did not quantify. So we did. So the whole paper focuses on the results on a test set, which we made sure is different. So we release a data set as well of training agents and test agents, which actually many people have built upon as well. So there are a couple of works from Shimon Wittenson's lab, which are building on this. But we did not quite quantify these morphologies as to how different is it the case that it will work. Yeah, I mean, we could do that, but we didn't do this. One reason is because we are doing zero shot generalization. So zero shot doesn't mean that it will always walk, but it provides a decent behavior. And now how do we measure what is decent, what is not decent? So we did not measure along that axis.
Thanks.
Okay. Now the question is, what are these messages learning? Are they capturing something meaningful? And in fact, in the biological agents, as I was showing this, okay, this always breaks for some reason. There are something called biological central pattern generators, like these cyclical patterns which you can find for motor neurons for walking in the body. And we found similar thing happens in our in our agents as well. So I plot here 2 things. On the x-axis, I plot the variation of the messages across the episode. On the y-axis, I'm plotting the projection of the message vector on one dimension. So it's the message vector across time step of the episode. In the beginning, the messages are random, so there is no variation. So it's just almost near 0. But as I train the agent, these messages start to capture these cyclical patterns automatically. And for Walker, this has 2 peaks. For Hopper, this has 3 peaks, which correspond to different shapes of the walking scenario. So what it is learning is that this coordination or the clock of the body is completely emerging from this learning process. Okay, and then somebody may ask, okay, and then we are also trying some real robot scenarios. So I don't have any results to show on the real robot yet, but we are trying with these robots which have shared motors at all locations and applying this. So here is one teaser result where the robot is very simple hexapod robot trying to walk. Yeah, I'm running late. How much time do I have? I think I took too many questions in between. Now I'm completely out of my.
So nominally 4 minutes, but I mean, I think if you want to go over, people would probably be happy to listen to you. But if you have other constraints, then that's understandable.
I mean, I have no constraint because after this I have meetings with all these folks in any way, so I can just go 10 minutes and then maybe cover this last part.
That's great.
Okay. So far we talked about goals and robots, but let's move to the dynamic task. So In all these cases, whether it's modular or it's curiosity, whatever is happening, there is one common theme, and that theme is as follows. You have an input value, could be an image or a state, and then you have this deep neural network policy, which acts and you will reward or whatever supervision. But this policy has always been a black box vector. So this is always black box, okay? And this kind of regime has been very successful across a wide variety of robotic tasks. And I also showed some of them like this knot tying and picking up. But there is one common thing across all these scenarios. Can someone tell me what is that common thing?
Can I try? I think the robot already knows where is the plane.
Yeah, that is all there. But the biggest problem that any robotics person has looking at these results is they say, wait, this is all completely static, or you can say quasi-static. What does it mean? It means that the robot can take 10 years between two actions and nothing would change. So it can just go and pick up one thing, then think for 1 year, then take another action, think for 1 year, another action. So there is this motion is very roboticsy, like it's too slow, and robot can take forever to act at each step, right? In fact, this notion of roboticsy motion is so typical that there is a dance form after after robotic motion. It's called the robot dance. But this is in contrast to how it works in case of humans or other biological agents, where the real world is very dynamic. So look at this, how you cut a vegetable. Like it's a very fluid motion. Like you are doing very fast. When you throw a ball or catch a ball, you have to reason about the whole dynamics. Like when you catch a ball in your hand, you have to talk about to reason the trajectory space of the robot as well as the object. You have to consider the momentum and forces. So you have to reason about the kinematics plus dynamics while doing things at a trajectory level. In contrast, all the deep robotic methods, they do not reason at the trajectory level. So the cost function or reward are for the trajectory, but the policy outputs actions at each time step differently, right? And you can operate in either raw, like torque, joint angle, position control, any control space, but you are acting independently at each time step. And that's why your motion looks like very roboticsy motion. So in order to solve dynamic tasks, our goal here is, can we build policies that reason directly in the trajectory space? Okay. And well, we take inspiration from the way things work in physics. So for instance, this notion of dynamical system or differential equations are used to describe the motion in natural phenomena like motion of fluids, motion of a flow of heat, the motion of planet moving around the sun. So can we use the same idea which describes the motion of planets to also describe the motion of a robot? Basically use differential equations to represent the motion. And this idea has been very popular in classical robotics, especially in the last 2 decades. And one example is this dynamic movement primitives, which are able to show very good results by representing motion as dynamical systems. And very dynamic results, like playing table tennis, flipping pancakes, writing on a board or something. And these methods capture dynamic tasks really well and can reason the trajectory space, but they require a huge amount of tuning and supervision. They need very close demonstration, and they're very sensitive to parameters and all that. And they do not work from high dimensional input like images. While these deep methods can work from high dimensional images and can work from weaker supervision like reward, but they do not reason at the trajectory level, and they do not, and they have difficulty with dynamic tasks. I would say they are not even shown yet with dynamic tasks. And it's very complementary. Like, how can we bridge the gap between these two paradigms? And this is what we did in one of our very recent work, which I'm quite excited about in general, this direction of kind of bridging the gap between the control methods and the learning-based methods. So what we do is we take this deep black box policy network and we unbox it. And we try to fit our dynamical system or differential equation solver inside the network. So this is very very simple idea and fully differentiable. So you take the state, you put this into a feature vector. Now we build after DMPs, which is the work from Stefan Schall from 2002, which represents two things at the trajectory level. It represents the goal and the shape of the trajectory. So where to go and how to go. So in the feature space, you output two vectors, G and W. And then you have the motion of the robot, which is the velocity, acceleration, position, velocity, and acceleration. And you define them via a differential equation, which is parameterized by goal and the shape of the trajectory. And then you solve this differential equation inside the policy. I just skip all this. And then you output all the actions towards the end. So what is happening overall at the overall picture here is the policy is outputting the raw actions, but those raw actions are for the full trajectory at once. So you output from AT to AT plus K, the whole trajectory at once. And how do you make sure that the whole trajectory is smooth? Is by fitting a differential equation inside the network. So let's give a quick intuition here. So here is this NDP thing. So let's say this is your starting position, this is your end position. So if you have policy which outputs at each action differently, like RL or any other policy, the trajectory will look like this. So you take one action, then second action, then third, then fourth. But if you represent something via differential equation, you actually get a very smooth trajectory from beginning to end. So it knows how to start at one position, it knows how to stop. Okay. And then they show a very smooth convergence to goal. And yeah, there are some more ablations I will skip in the interest of time and not go there. But yeah, they are robust to the different shapes and different sunny positions. And the key part that we have in this work is that they are super easy to implement. Basically, just 5 to 7 lines of code to be added to your default RL or imitation learning method, and it just works. So in case of results, let's show some simulation results first. We tried a bunch of environments. Again, since it's a paper already at NeurIPS, it was a spotlight. So of course it beats the baseline. So this is not surprising. So let me just go through it. Beats the baseline, beats the baseline. And here is my favorite part here. So let's see how can we learn this dynamical system or dynamic task from images. And here is an example of our method and other baselines. Now it's very hard to see on this simulator. So let me show you real robot results. So here is a robot trying to do the task of writing on the board, and a brief disclaimer that it is a bit. Oops. Let's see here. How well does it do? So there is a very weird noise coming up because it is dragging the it drags the marker across the board, but it is able to draw these digits in a very smooth manner. And this is a follow-up to this idea, but we have a hierarchical framework. And let's see some results here. Sun coming in my slide. Okay, so here we perform a very thorough experimentation on hardware with this kind of approach and show a wide variety of results across a wide variety of domains. So, so let's see what we are able to do. So given a demonstration in here, so we collect the demonstration, let's say the task of scooping. So this demonstration is collected by hand in a kinesthetic manner, and then we just replayed it. Then we train these NDPs from images from those demonstrations. On the left, you see a baseline, which is guided policy search. And you can see how much the robot is shaking in trying to do this task, and it also fails to do it properly. On the right, this is our method, which is a very smooth and fluid motion. Like you don't see this jerky, these jerky behaviors. And this is the same policy, and the difference is of a dynamical system inside the policy. Again, a demonstration, a replay of the demonstration that was collected, and then this is happening from the image space. So we train an image space policy. On the right here, you see the image that the robot sees. It is again a baseline. So it has difficulty in solving the task, but also difficulty when the things change. And on the right, here is our method, which can, let me try to skip it. Again, the motion is very fluid and the arm can actually, so you don't feel the jerk or any differences in the arm. I think this is more visible in the digit drawing example, which will come next. I don't know how to skip the video here. It is not showing me the bar. Okay, here, this one. So here the task is to draw on the whiteboard. And on the left, you see a normal policy. So given the image at test time, so robot sees this image. And this is a test time, a new example, which the robot was not trained on. You can see how jerky the jerky behavior now properly shows up. On the right, the behavior is very smooth, and given a new digit, it can actually make a very smooth code at test time. Okay, so this was the last part, and the last part is very fast here, just sim to real. We have this new work coming up in ICRA, where we try to kind of automate the sim to real process. Okay, this is not moving very fast. Like currently, sim to real is being sold as a very big idea that, oh, we can just transfer from simulation to real world. But if you go back to papers and read sim to real papers and go to their appendix, not the paper, but the appendix, you will find the range of the number of parameters that everyone varies in simulator to show good results at test time. And it's daunting. Like it's a lot of parameters, a lot of variation that people try in the real world to adapt. And one of the recent work that is upcoming, we had this auto-tuning sim to real transfer where we learn how to tune the simulator by keeping the reality in the loop in an automatic manner. And this again is this is inspired by one of the work from Dieter Fox's lab, but their work works from state space, and here it is all happening from images and requires no instrumentation in the real world. So here, like we train a policy from simulator, and when we try this, it completely fails to work. But then we have this automatic process which looks at the real world and adapts the simulator on its own. And as you do multiple iterations, towards the end, it starts to do tasks in the real world, which it was not able to do before. So here, the general idea is look at the real data, and instead of changing your policy, change your simulator so that your simulator becomes closer to the reality, not other way around. Okay, so again, you can do multiple things in the real robot. So one last part before I just end the talk is that so far I have been all talking about these models which are trying to capture how the world works, but they have been very simple. I think they are working from 2D images without any reasoning about the 3D world. And one of the research interests of mine currently is also to somehow incorporate the 3D information about the world from 2D images. So, and this is one of the work which we just released, where we take the single image of a scene and we try to imagine how the scene looks like in 3D. So given a single image at test time, no other image, and you can imagine how this world looks like in 3D and actually generate very novel views and go into the image and see it from different perspectives. And this is all happening from a single image. And the eventual goal is to bring these 3D imagining models in the robotic domain and do it together. This is my vision hat, which will come up soon to, or we're working on the extension to apply to robotic scenarios as well. Okay, so this is it. This is a summary. I already talked about it, and everything is available on the website with code and all the details. I can take questions now.
That's amazing stuff. I lost track a little bit of the chat and who still has questions. So I guess anybody who has a question, just go ahead.
Hi, Deepak. Thanks for the talk. I had a couple of questions. The first one is, when you talked about transfer of policies across different hardware, do you think the approach that you presented could also work if the underlying physics such as gravity or friction coefficient changes?
Yeah, I'm not sure if, I mean, at least if you change it at training time, yes, then it is possible. So we do not have the underlying physics changes, but actually in one of the works, in the new rips before that, we did show generalization to new terrains. So I was showing to new robots, not to changing environments, but we did show, let me see if I can find it here. So we did show these results. For some reason, it is not showing me the browser, So here we train these robots for the task of locomotion. They were trained on a bumpy surface like this, but then since a bumpy surface captures a lot of dynamics or a lot of variations in the environment, we could generalize these robots from the bumpy surface to, let's say, hurdles or these stairs or things like that. And this is all happening because the learning was fully modular. So a bumpy surface for a small robot is same as bumpy surface or a hill for a bigger robot and things like this. But there was no gravity variation here. And I don't know if it is easy to adapt to a new gravity in a zero shot manner. And but you can fine tune from there, and then it can probably learn faster. Like, I don't know if we go to Mars, like astronauts go to Mars or Moon or other places, they actually practice before going there how to walk in less gravity or no gravity. And so I don't think it's a zero shot even for the biological agents. So it won't be zero shot, but it can actually, I hope it can at least fine tune and learn faster.
Okay. The second question I had was, you mentioned about like having smooth policies versus having jerky policies, right? Yeah. Is there a way to quantify the smoothness of a policy?
Well, so what we showed that if you embed the dynamical system inside the policies, it makes the policy smooth, but that's not the only thing. It actually also improves your task performance. So all the baseline that you see were purely apples to apples, with the only difference of the dynamical system. So the policy was not only smooth, it was doing the task better. So our evaluation was mostly on how well can you do the task. But I emphasized the smooth part, and that was, I think, as a byproduct. We didn't quantify it easily. It's not quite easy to quantify. I mean, it's a qualitative thing. But one way to quantify is to do tasks which require smooth motion and then see how well can you do those. So like pouring or scooping, it requires the thing to be smooth, because if you're scooping some elements from the bowl, if you don't do it fast enough, then they will fall into the bowl itself. Like in your, they won't come into because it's a very flat spatula. It's not like I don't know what is the term for this. It's not like a very deep spoon. It's a flat spatula, so you have to do it in a very smooth manner to get these things out of the bowl. So we measured success rate, and I think that has some correlation with the smoothness. But yeah.
Okay, thank you.
There was another question from Ethan in the chat. If someone handed you a very large video generative model that had been trained on all of YouTube such that it had become extremely good at predicting a minute into the future, how would you use it for robot learning? Ooh, it's a real philosophical question.
Yeah, I would just do planning. I mean, if you could actually predict a minute, you could just plan for anything and just keep applying it recursively. But here there is one issue though. How do I put it? Think of it this way. Let's say you have never held a tennis racket in your hand ever, but you're allowed to watch thousands and thousands of hours of YouTube videos on how to play tennis. Or you can watch Roger Federer 24/7 for a year. I bet you can still not play tennis without ever interacting with the world, right? You cannot become like Roger Federer by watching Roger Federer. So imitation is a very important part of learning, but it is nowhere sufficient. It is necessary, but not sufficient. So I do not think that will just solve all the problems, even if you could do that.
Is it even necessary?
It could
it's
be
nice, but is it necessary? Like,
necessary.
I could probably, like, Roger Federer didn't watch Roger Federer play tennis to learn how to play tennis.
Correct. So what I think it is necessary for the diversity part. So for instance, like one of the key reason for success of deep learning and learning in vision and language is that we could just act on a very diverse pool of data. But let's say if I could somehow know how to move my own body, my own hands, and do interesting thing, and somehow I can learn how to map my own actions to the video of others, then I could just parallelize in a crazy manner. Like you could just watch hundreds of hours of kitchen videos. Like there are data sets from vision community on epic kitchens where they have like, I don't know, 20 million videos or something, or 2 million of people doing diverse things, which I think will be very hard for at a level where the robotics will be very hard to scale to. So I think in that sense it's necessary, but for doing one task very well, it's not necessary. Yeah. If you want to become expert at tennis and not being able to open the door,
Assume the goal is you want a robot to be an expert at just like a zillion tasks, or like the max amount of tasks conceivable.
Yeah, yeah. I didn't show this, but we actually have a work where we go from human videos to enacting and then simulating. It's called third-person visual imitation learning, where we see a third-person video, but then again, over there we don't just have the video; we also act in the world to map the video to your own frame.
There's also some I think from neuroscience literature or people studying this type of things can say that seeing someone doing something that we've already practiced a bit has some effect of reinforcement, right? Like the brain during some sleep or breaks can have this type of reinforcement loops happening there and reinforcing the gestures or the skills that the agent has developed already.
Yeah. No, yeah. I think it is helpful, but it's probably not sufficient. Yeah, and as Liam was saying, it's probably not necessary for one task scenario. To like, I mean, there are robots already which assemble your cars, so and they are probably not watching YouTube. So it's probably okay. But if those robots were to also do something else, that's completely impossible right now.
Yeah, sounds good. So just in the interest of time, and I see that you've got a packed schedule lined up for the next couple hours. I just want to thank you again for this amazing presentation. And yeah, for anyone that has questions, there's like a spreadsheet that we've been sort of using for assigning schedules for meetings. So feel free to put your name, and there's still one vacant spot. So again, Deepak, it was really nice. I really enjoyed listening to the talk, and I guess all of the other students got to ask a lot of questions as well. So yeah, looking forward to seeing more exciting work from your group.
Thank you.
Awesome. Thanks so much, Deepak.
Yeah, we have some new things which we did not cover in the meeting, but I showed it to Krishna and other Florian in the previous thing. Yeah. Okay.
Yeah, that looks super cool.
Cool. All right. So see you everyone, and I'll send a link for the meetings. Can I send my own Zoom link? I think there was.
Yeah.
Okay. I'll put in the spreadsheet directly. All right. Bye.
Great. Thanks.
Thank you.